All right, now what we're going to do is we are going to look at some examples of implicit differentiation. So notice here that my x and my y are kind of scrambled together. There's no way for me to solve for y. So I'm going to have to use implicit differentiation. I don't know why this keeps auto-focusing, and I'm super sorry. I tried to fix it. I will try not to move my hands too much. All right, so let's look at taking the derivative of this guy. So, well, the derivative of y is 1, and remember, whenever I take the derivative of y, to get it into the right units of measurement, I need to multiply it by dy over dx. Equals, all right, so then the derivative of 5x squared, that's going to be 10x plus, and the derivative of cosine of y, so if I take the derivative of this guy with respect to y, is going to be negative sine of y. Now remember, I took the derivative with respect to y, so if I want to change this derivative so that it's with respect to x, I need to multiply it by that dy over dx. Okay. Now what I need to do is that I need to solve for dy over dx so that I can get that nice derivative relationship. So I'm going to move everything over to one side that has a dy. So I'm going to go ahead and add the sine of y, dy over dx to both sides. So I'm going to have dy over dx plus sine of y dy over dx equals 10x. Now, since I have a dy here and a dy here in this term, what I can do is I can factor it out. So I'm going to have dy over dx times, well, if I divide dy over dx by itself, I'm going to be left with 1. If I divide sine of y by dy over dx, I'm going to be left with sine of y equals 10x. Now, if I want to get that dy over dx by itself, I need to divide both sides by 1 plus sine of y. So 1 plus sine of y, divide this side by 1 plus sine of y, and we will have dy over dx equals 10x divided by 1 plus sine of y. And that would be the derivative for this function. All right, let's look at another example. Let's look at y squared equals sine of x plus 4e to the 3y. All right, so let's find the derivative of this guy. So instead of using dy over dx this time, so instead of using dy over dx, we can actually write y prime. They mean the exact same thing. I just think that one's a little bit simpler. It's totally up to you. If you're worried that you're going to get your y's confused if you write y prime, then you can just continue to write dy over dx. All right, so let's see. You need to take the derivative of y squared with respect to y, so it'll be 2y. Now remember, I took the derivative with respect to y, so to make sure that I'm still taking the derivative with respect to x, I need to multiply it by y prime, equals the derivative of sine, cosine, plus the derivative of 4e to the 3y, that is going to be 12e to the 3y. Don't forget, I took the derivative with respect to y, so I need to multiply it by y prime. Now what I want to do is I want to get all of my y primes on one side and everything else on the other. So what I'm going to do is subtract this 12e to the 3y from both sides. Times y prime. So I will have 2y times y prime minus 12e to the 3y times y prime equals cosine of x. Alright, the reason I move all the y primes over to one side is now every term has a y prime, so I can go ahead and factor that out. So I have y prime times 2y minus 12 e to the 3y equals cosine of x. Now, some of you may be thinking, well, couldn't you take the 2 out of here? Well, we could, but remember, our goal is to get that y prime by itself, so we don't want to factor out anything but the y prime for right now. So now we need to divide both sides by 2 minus 12 e to the 3y, so we can get that y prime by itself. 2y minus 12 e to the 3y. And we will end up with y prime equals cosine of x divided by 2y minus 12 e to the 3y. That would be our final answer.